Number 10. Aerosolized bodily fluids. In the familiar environment of Earth, human bodily fluids behave predictably. Tears roll down cheeks, sweat drips from skin, and saliva stays where it belongs. But in the microgravity environment of space, these ordinary secretions transform into something potentially deadly. Without gravity's pull, they don't fall, they float, forming spherical droplets that drift through spacecraft cabins like microscopic biological mines. NASA first documented this phenomenon during early Gemini and Apollo missions, when astronauts reported floating globules of water that would splinter into smaller droplets when disturbed. What seemed merely curious became concerning when scientists realized that all human fluids, tears, sweat, saliva, vomit, urine, and even blood, follow the same physical laws in space. These aerosolized droplets can persist for hours, even days, creating invisible hazard zones throughout a spacecraft. When released from the human body, they carry whatever microorganisms the person harbors, potentially pathogenic bacteria and viruses that can remain viable in the suspended state. One astronaut's common cold can rapidly become everyone's infection when virus-laden moisture hangs in the air like a biological fog. But the danger extends beyond biological contamination. These fluid spheres are attracted to surfaces through capillary action, leading them to electronic equipment and air circulation systems. In 2013, an International Space Station spacewalk had to be abruptly terminated when a water leak in an astronaut's helmet formed a growing blob that threatened to drown him in the vacuum of space. A bizarre juxtaposition of drowning hazards in an environment without oceans or lakes. What makes this phenomenon particularly insidious is its origin in normal human physiology. Every breath you exhale in space releases microscopic water droplets. Every time you wash, invisible clouds form. Your body itself becomes a source of potential hazard in the void, turning the most fundamental aspects of being human into silent threats that linger, invisible, waiting for the wrong moment to interfere with critical systems or find their way into another astronaut's lungs. Number 9. Temperature extremes. The void between worlds harbors one of the most dramatic thermal environments in the universe. In direct sunlight, unshielded surfaces in space can reach temperatures of positive 250 degrees Fahrenheit, hot enough to boil water and melt lead. Step into shadow, and those same surfaces plummet to negative 250 degrees Fahrenheit, colder than the coldest place on Earth. This 500-degree swing can happen in seconds, across distances measured in inches. The brutal reality of space's thermal environment became clear during the early space missions. When Apollo astronauts described the lunar surface, they noted how the sun-facing side of rocks was hot enough to burn through gloves, while the shadowed side remained cold enough to shatter like glass. Their spacesuits, technological marvels of the 1960s, struggled to maintain survivable temperatures despite weighing nearly 200 pounds. What makes space temperature extremes particularly deadly is the absence of air. On Earth, air acts as an insulator and conductor, distributing heat and moderating temperature changes. In the vacuum of space, heat transfers only through direct radiation and conduction. Touch a sun-heated metal tool with an unprotected hand, and your skin will flash fuse to it before you can react. Brush against a shadowed surface, and your tissue can freeze solid in seconds. Modern spacesuits use complex systems of water circulation, reflective coatings, and layered insulation to maintain a habitable microenvironment. But these systems represent a single point of failure between life and death. During a 2013 spacewalk, Italian astronaut Luca Parmitano's cooling system malfunctioned, causing his body temperature to rise dangerously, while simultaneously allowing condensation to form inside his helmet, demonstrating how quickly thermal regulation failures cascade into multiple life-threatening emergencies. The human body evolved in Earth's relatively stable thermal environment. In space, an unprotected human would simultaneously experience third-degree burns on surfaces facing the sun and flash-freezing tissue death on shadowed sides. A thermal trauma beyond anything medical science has categories to describe. We remain fundamentally incompatible with the basic thermal nature of the cosmos. Number 8. Toxic space dust. When Apollo astronauts returned to their lunar module after moonwalks, they brought something unexpected with them. A fine, dark powder that clung to everything it touched. This lunar dust proved surprisingly problematic. It smelled like spent gunpowder, irritated their eyes and lungs, and wore down seals on their equipment. What the astronauts didn't know was that they were experiencing humanity's first contact with one of space's most insidious killers. Unlike Earth dust, which has been weathered by wind, water, and biological processes for billions of years, extraterrestrial dust never undergoes erosion. The result is microscopically jagged particles with edges sharp enough to slice through cell membranes. Lunar dust consists primarily of tiny shards of glass created by meteorite impacts, while Martian dust contains perchlorate and reactive chemicals that can damage the thyroid gland and nervous system. What makes space dust particularly dangerous is its perfect storm of physical and chemical properties. The particles are so fine, many less than 20 microns in diameter, that they easily bypass the body's filtration systems. Their electrostatic charge, created by solar radiation, causes them to cling tenaciously to spacesuits, equipment, and lung tissue. Once inside the respiratory system, these microscopic daggers become embedded and begin their destructive work. Researchers at NASA have identified a condition they call dust pneumoconiosis, where extraterrestrial dust particles cause progressive scarring of lung tissue. Unlike Earth-based silicosis, which develops over decades, space dust can trigger inflammatory responses within days or weeks of exposure. Simulations suggest that a long-duration Mars mission could result in enough dust exposure to permanently reduce lung function by up to 20%. The most troubling aspect of toxic space dust is its unavoidability. It's the very ground beneath an astronaut's feet, the surface of everything they'll touch, and the potential building material for future habitats. As we plan longer missions to the Moon and Mars, we face an uncomfortable truth. The very worlds we seek to explore are covered in a substance that silently shreds human tissue from the inside out. How do you colonize a planet when its soil is toxic to human life? Number 7. Cognitive deterioration. In 2017, researchers examining the brains of mice exposed to cosmic radiation made a disturbing discovery. The rodents showed significant neurological damage, with impaired memory, learning deficits, and anxiety-like behaviors that persisted long after exposure. These changes mirrored what astronauts have been reporting anecdotally for decades, a subtle but progressive decline in cognitive function that scientists now call space brain. Unlike the immediate obvious dangers of space, cognitive deterioration unfolds slowly and insidiously. The human brain, despite its remarkable capabilities, evolved under the protective shield of Earth's magnetosphere and atmosphere. In space, it encounters a barrage of high-energy particles, primarily galactic cosmic rays, that can penetrate spacecraft hulls and protective equipment. These particles cause cascades of secondary radiation inside the brain tissue, triggering inflammation and damaging neural connections. What makes space-induced cognitive deterioration particularly troubling is that it may not become apparent until after the mission. Studies of returning astronauts show subtle changes in executive function, spatial orientation, and decision-making ability. Some experience persistent vision problems due to intracranial pressure changes. Others report personality shifts noticed primarily by family members, increased irritability, emotional detachment, or unusual risk-taking behaviors that weren't present before flight. The combination of radiation exposure, sleep disruption, isolation, and microgravity creates a perfect neurological storm. The brain's glymphatic system, which clears waste products during sleep, functions poorly in space. Circadian rhythm disruption from witnessing 16 sunrises and sunsets daily further impairs cognitive recovery. Even the redistribution of fluids toward the head in microgravity may contribute to long-term neural damage. As space agencies contemplate missions to Mars, requiring up to 3 years of continuous space exposure, the specter of cognitive deterioration looms larger. Advanced shielding can block some radiation, but not all. Pharmaceutical neuroprotection remains experimental. The disturbing reality is that extended space missions may fundamentally alter who astronauts are, transforming not just their bodies, but their minds in ways we're only beginning to understand. The person who leaves Earth may not be the same person who returns, even if they appear unchanged. Number 6. Opportunistic microbes. In 2006, astronaut Anousheh Ansari developed a urinary tract infection aboard the International Space Station. What should have been a simple medical issue on Earth became a potential crisis in orbit. The bacteria responsible, typically manageable with antibiotics, had adapted to the space environment in ways doctors hadn't anticipated. It was one of the first documented cases of a phenomenon scientists now consider one of space travel's most overlooked dangers: microbial mutation and adaptation beyond Earth's atmosphere. Humans carry trillions of microorganisms with them into space, bacteria and fungi that have evolved alongside us for millennia in Earth's gravity and radiation environment. But in the crucible of space, these microbes encounter evolutionary pressures unlike anything in their 4 billion year history. Studies aboard the ISS have shown that common bacteria like E. coli and Staphylococcus aureus undergo genetic changes at accelerated rates in microgravity, activating genes that increase virulence, antibiotic resistance, and biofilm formation. What makes opportunistic microbes particularly insidious is their dual adaptation advantage. While human immune systems weaken in space, with T-cell function decreasing by up to 40% during long missions, bacteria simultaneously become more aggressive. This creates a dangerous convergence where pathogens grow stronger just as our defenses grow weaker. A 2019 study found that Staphylococcus aureus cultures grown on the ISS developed antibiotic resistance 3 times faster than identical cultures on Earth. Even more concerning, these adaptations don't necessarily revert when microbes return to Earth. The genetic changes induced by space exposure can become permanent, creating new variants of familiar pathogens that could spread among the general population. Some researchers fear that a truly novel space-adapted superbug could emerge from long-duration missions, potentially bringing back pathogens fundamentally different from anything our immune systems or medical treatments have encountered. The ultimate irony of space exploration may be that the greatest biological threat doesn't await us on alien worlds, but travels with us from the beginning. Ordinary microbes we've lived with peacefully on Earth, transformed by cosmic forces into something our bodies no longer recognize. How do we prepare for enemies that evolve faster than we can study them, using our own bodies as their evolutionary laboratories? Number 5. Vacuum-Induced Bubble Embolisms. In 1965, during a ground test of a spacesuit, a technician was accidentally exposed to vacuum conditions when his suit leaked. Though he survived, he reported feeling the saliva on his tongue begin to boil before he lost consciousness. This disturbing phenomenon results from the fundamental nature of space itself, the absence of atmospheric pressure that allows dissolved gases and bodily fluids to rapidly form bubbles, similar to opening a carbonated beverage. What makes vacuum exposure particularly deadly isn't just the immediate effects, but the delayed consequences that can manifest years later. When humans experience rapid decompression, nitrogen and other gases dissolved in the bloodstream form bubbles that can travel throughout the circulatory system. These gas emboli can block the blood vessels in the brain, heart, and lungs, causing immediate damage. But some smaller bubbles may resolve without immediate symptoms, leaving microscopic injuries that only become apparent over time. Medical researchers studying high-altitude pilots and astronauts have discovered a troubling pattern of silent strokes, tiny areas of brain damage caused by microbubbles that form during decompression events. These lesions may not produce noticeable symptoms initially, but can contribute to cognitive decline, memory problems, and increased stroke risk later in life. Similarly, bubbles that temporarily lodge in coronary arteries can trigger small areas of heart muscle death that weaken cardiac function over decades. Even more concerning are the bubbles that form in cerebrospinal fluid surrounding the brain and spinal cord. These can cause pressure changes and inflammation that damage delicate neural tissues, potentially leading to chronic pain syndromes and neurological disorders that emerge years after space travel. The blood-brain barrier, which normally protects neural tissue, becomes temporarily more permeable during decompression events, allowing harmful substances to reach brain cells. The human body evolved under the constant pressure of Earth's atmosphere, with biological systems that assume this pressure will remain stable throughout life. In space, even with the protection of spacecraft and spacesuits, pressure changes remain an unavoidable risk. Every airlock cycle, every spacesuit donning, every potential micrometeoroid puncture represents an opportunity for gas bubbles to form within the body. Some astronauts may already carry these microscopic time bombs in their tissues, unaware that their journey to space has programmed a delayed physiological countdown. Number 4. Micrometeoroid Impacts. In 2016, ESA astronaut Tim Peake photographed a troubling discovery on the International Space Station, a 7mm pit in one of the observatory windows. The cause wasn't a structural failure or manufacturing defect, but something far more unsettling. A paint fleck, smaller than a grain of salt, traveling at 17,000 miles per hour. This tiny impact, barely noticeable on Earth, had enough kinetic energy in orbit to damage multi-layered reinforced glass, designed to withstand the harshest conditions of space. What makes micrometeoroids particularly terrifying is their perfect combination of inevitability and lethality. These particles, most smaller than a millimeter across, are ubiquitous throughout the solar system. Some are natural, fragments of asteroids and comets that have drifted for billions of years. Others are human-made microscopic debris from deteriorating satellites. Regardless of origin, in the vacuum of space, they maintain velocities that transform them into hypersonic projectiles with the penetrating power of high-caliber bullets. The danger they pose becomes clear when examining their physics. A 1mm metal sphere traveling at typical orbital velocity carries the kinetic energy of a bowling ball, moving at 60 miles per hour. The resulting impact doesn't just puncture materials, it vaporizes both the projectile and target into expanding clouds of plasma that can damage surrounding systems and create secondary projectiles inside spacecraft or spacesuits. Despite decades of engineering efforts, there is no perfect defense against these cosmic bullets. The ISS incorporates Whipple shields, space layers designed to break up incoming particles, yet still sustains numerous impacts yearly. NASA estimates that the Space Shuttle windows required replacement after every few missions due to micrometeoroid damage, with each window displaying dozens of microscopic impact craters after returning from orbit. For astronauts conducting spacewalks, the threat takes on a more personal dimension. The outer layer of a modern spacesuit can stop particles up to about 0.1 millimeter, but larger impacts would penetrate all the way to human tissue. The void between worlds is filled with countless invisible projectiles, each capable of ending a mission or a life in a fraction of a second, with no warning and no sound. In the silence of space, how do you defend against dangers you cannot see, hear, or anticipate until they've already struck? Number 3. Space debris collisions. On February 10, 2009, two satellites collided 500 miles above Siberia, the American communications satellite Iridium-33 and the defunct Russian military satellite Cosmos 2251. The impact occurred at over 22,000 miles per hour, completely destroying both objects and creating a debris cloud of over 2,000 trackable fragments and countless smaller pieces. It was the first major collision between two intact satellites, and a grim demonstration of a threat that grows more severe every year. Unlike natural space hazards, orbital debris is entirely human-made, a growing cloud of technological shrapnel surrounding Earth. Since Sputnik's launch in 1957, thousands of rockets and satellites have been placed in orbit. Many remain there long after their operational life, gradually deteriorating or occasionally exploding when leftover fuel tanks rupture. Each such event releases thousands of new fragments, from bus-sized rocket stages to microscopic particles, all traveling at velocities exceeding 7 kilometers per second. What makes orbital debris particularly concerning is its potential for cascading effects. In 1978, NASA scientist Donald Kessler proposed what is now known as the Kessler syndrome, a scenario where the density of objects in low Earth orbit becomes high enough that collisions between objects generate new debris faster than natural atmospheric drag can remove it. The result would be a self-sustaining chain reaction of collisions, potentially rendering entire orbital bands unusable for generations. Evidence suggests this process may already be underway. The U.S. Space Surveillance Network currently tracks over 27,000 objects larger than 10 centimeters, but estimates suggest there are more than 100 million pieces larger than 1 millimeter, each capable of damaging or disabling operational spacecraft. Between 2015 and 2022, the number of active satellites in orbit more than quadrupled, with companies launching vast constellations of small satellites, exponentially increasing collision risks. The cruel irony of orbital debris is that humanity has created a prison around our own planet, a growing barrier of our own technological waste that threatens to trap us on Earth just as our space ambitions expand. The void above our atmosphere, once pristine and empty, now contains the fastest and most numerous man-made hazards ever created, circling our world in an endless hypersonic derby of potential destruction. Number 2. Extreme radiation. In 2003, instruments aboard the International Space Station recorded an alarming event. Radiation levels inside the habitat suddenly spiked to more than 100 times normal background levels. The cause was a massive solar flare, one of the largest in recorded history. Had astronauts been conducting a spacewalk during this event, they would have received their entire yearly radiation allowance in under an hour, potentially suffering acute radiation sickness despite their protective equipment. What makes space radiation particularly insidious is its invisibility and variety. Unlike radiation sources on Earth, which can be shielded or avoided, cosmic radiation permeates space in forms that penetrate even the most advanced materials. Galactic cosmic rays, atomic nuclei stripped of their electrons and accelerated to near light speed by distant supernovas, carry energies millions of times greater than medical X-rays. Solar particle events unleash storms of protons that can overwhelm spacecraft shielding. Together, they create an invisible, ever-present sea of energetic particles that silently damages living tissue at the cellular level. The effects on the human body are profound and cumulative. High-energy particles don't just damage cells, they shatter DNA strands into fragments, creating complex breaks that the body struggles to repair correctly. This leads to chromosomal abnormalities, increased cancer risk, and accelerated aging. Studies of Apollo astronauts revealed higher rates of cardiovascular disease decades after their missions, with researchers linking these conditions to their brief radiation exposures beyond Earth's protective magnetosphere. Even more concerning are the acute effects during long-duration missions. Without Earth's magnetic shield, astronauts traveling to Mars would face radiation doses equivalent to receiving a full-body CT scan every 5 days for 3 years. Visual phenomena called light flashes occur when energetic particles hit the optic nerve or visual cortex directly, creating phantom visual disturbances. More seriously, radiation exposure during deep space missions could damage the central nervous system enough to impair cognitive function and reaction time, precisely when astronauts need these abilities most. The cruelest aspect of space radiation is that there is no perfect defense. Traditional shielding materials like lead or water merely fragment high-energy particles into secondary radiation that can be even more damaging to tissue. Pharmaceutical radioprotectants remain experimental and cannot fully prevent damage. As we venture deeper into the solar system, how do we protect against a fundamental force of the universe that passes through almost everything we can build? Number 1. Vacuum exposure. In the vast theater of cosmic hazards, none is more fundamental or immediately lethal than the vacuum of space itself. The absence of pressure, a perfect vacuum just one breath away from any astronaut, creates the most hostile environment humans have ever attempted to survive. While Hollywood depicts explosive decompression and instant freezing, the reality of vacuum exposure is both more complex and more disturbing than fiction suggests. Contrary to popular belief, the human body does not explode when exposed to vacuum. Instead, it undergoes a cascade of physiological failures that occur with terrifying rapidity. Within the first second, the water on exposed membranes, eyes, mouth, airways, begins to boil at body temperature due to the absence of pressure. The lungs, if not emptied during decompression, rupture as trapped gases expand. Oxygen dissolved in the bloodstream begins forming bubbles, similar to a dangerous case of decompression sickness. Consciousness fades within approximately 15 seconds as oxygen-depleted blood reaches the brain. The heart continues beating for up to 2 minutes, circulating increasingly deoxygenated blood through a body rapidly swelling to nearly twice its normal size as tissues absorb the gas expanding within them. Without intervention, death follows from asphyxiation and circulatory collapse. The window for survival is vanishingly small. NASA's research suggests that if rescue and repressurization occur within about 90 seconds, recovery might be possible, though not without lasting damage. The longest documented human survival of near-vacuum conditions occurred during a 1966 NASA spacesuit testing accident, when technician Jim LeBlanc's suit depressurized. He remained conscious for approximately 14 seconds before collapsing. His last memory before losing consciousness was feeling the saliva on his tongue beginning to boil. What makes vacuum exposure particularly sobering is its omnipresence in space. Unlike other hazards that might be avoided or mitigated, the vacuum waits everywhere beyond the fragile shells of our spacecraft and habitats. It is the default state of the cosmos, a fundamental condition of space itself. Every spacesuit, every habitat module, every spacecraft window exists as a tenuous barrier between life and the void, just millimeters thick in some cases. In our quest to explore the universe, we face the ultimate irony. Space itself is the deadliest hazard of all, a hostile emptiness that surrounds us at every moment beyond Earth, quietly waiting for the slightest failure in our protective systems to reclaim us into the eternal nothing from which all life struggles to maintain its brief, ordered existence. If you want to see more videos like this, click the video on screen now and make sure to subscribe.